Welcome back. This is the second part or the second video on section 1.1 in which we are going to formulate and prove the Arzela-Ascoli theorem about relative compactness in the space Cxy. Okay. So one necessary condition for relative compactness turns out to be a condition of continuity, but which is stronger than usual continuity. It's called equicontinuity. Equicontinuity is a kind of collective continuity, if you like. So if you have a set of functions, a subset of Cxy, we say, so we denote this collection by calligraphic F. We say that this collection is equicontinuous at the point x0 if this condition holds. For every positive number epsilon, I can find a positive number alpha, such that, pay attention to the order of the quantifiers. For every f in the collection and for every x in the space, if the distance between x and x0 is less than epsilon, then the distance between their images under any f in the collection is less than epsilon. So you see that it resembles, so actually here we find that the alpha depends on epsilon and x0. Okay, and not on f and not on f. So it's a kind of uniform in f or collection-wise continuity, if you like. Okay, and now I'll give examples of such. Not every collection of continuous functions satisfies this property. So this implies in particular that each individual f is continuous. Okay, but we can choose the alpha the same for every f. Okay, not trivial at all. And we say that this collection is equicontinuous on the space X if it's equicontinuous at every point of the space. And we have a still stronger notion, which is uniform equicontinuity, where actually we can take the alpha depending only on epsilon, okay, and not on epsilon and x0. So same thing as so here actually we have uniform continuity of each member, but this happens in a uniform way with respect to the elements of the collection. Okay. And of course, as you probably know, that instead of less than epsilon, I can put less or equal than epsilon, and instead of less than alpha, I can put less or equal than alpha. You know that because if it's strictly less, it's less or equal. And if it's less or equal than epsilon, then it's less than strictly than 2 epsilon. Okay, so once again, if you want to prove such condition, you don't need to precisely have 1 epsilon. Okay, if you prove that this is less than 10 epsilon, it's okay. Okay, so example, if you take X to be the compact space 0, 1 and Y to be R with the usual distance, and consider the collection calligraphic F of all continuously differentiable functions on 0, 1 whose norm of the derivative is less than 1. So the supremum of f prime of x is less than 1. Okay. So otherwise stated is the set of C1 functions whose derivative is bounded in absolute value by 1. And I claim that this collection is equicontinuous, uniformly actually. Why? This is a consequence of the mean value theorem. Because we know that for every t and s in 0, 1 and for every s, or for every f, the distance between fs and ft is less than the maximum of the derivative times s minus t, but this is less than 1. So we have here this collection-wise continuity. So, or actually each f is Lipschitz continuous, but this happens with the same constant 1. Okay, so this is stronger even than uniform equicontinuity. Okay, it's Lipschitz equicontinuity, if you like. So in the definition, we can take alpha equal to epsilon. If this is less than alpha, then this is less than epsilon, and so this is less than epsilon. And this happens, so alpha equal epsilon here. So it's independent on x, it's independent on f. Okay, and exercise, a little bit challenging. If the space is compact, then equicontinuity of a collection of continuous functions implies uniform equicontinuity. So it's like the result saying that a continuous function on a compact set is uniformly continuous. Here we have equicontinuity on X on a compact set implies uniform equicontinuity. Of course, uniform continuity is stronger than continuity, but the converse is true if the space is compact. And there are several ways to prove this. I suggest that this is a little bit challenging, but it constitutes a very interesting and typical exercise in analysis. So write the condition of uniform equicontinuity and negate it. We shall do something similar now. Okay, and see what happens. Okay, and next result tells us that equicontinuity is a necessary condition for relative compactness. So if you have a compact metric space capital X and a subset calligraphic F of the space of continuous functions from X to Y, if this set is relatively compact, then it's necessarily equicontinuous. So we found one necessary condition. Okay, why this is true? We reason by contradiction. Okay, so let us negate the condition of equicontinuity at x0. So you have to negate the condition before. Okay, so for every epsilon there exists alpha, for every f, for every x, etc. So for all becomes there exists becomes for all. So there exists some positive number epsilon 0, such that for every alpha positive there exists an element in the collection, there exists a point in the space, such that the distance between this point and x0 is less than alpha, but the distance between their images under this f is bigger or equal than epsilon 0. So this is just the usual negation. Now I cannot change the epsilon 0, it's given, but I have a freedom in choosing alpha. So I can choose in particular alpha equal 1, alpha equal 1/2, or anything, any sequence converging to 0. So take epsilon, so alpha equal 1, 1/2, etc. Then for each n, we find an element that depends on n, so fn, and we find an element xn. So I have two sequences now, a sequence in the collection of functions and a sequence in the space. Such that what? The distance between xn and x0 is less than 1 over n, but the distance between their images under fn is bigger or equal than x. So we have now a function in x and a function in fn. And we shall, so now if you look at this condition, this implies that xn converges to x0. Okay? First thing. Now, we assume that this collection calligraphic F is relatively compact. So according to what we said in the previous video, Fn has a subsequence that converges in the space Cxy. Okay, so of course it's still in the space because still we know that it's continuous. Okay, but it's not necessarily an element of the sequence. Okay. So, but convergence in Cxy is precisely uniform convergence. Okay, and we know that the limit must be continuous. Okay, so now let us use a trick instead in order to simplify the notation. So instead of writing fnk, we can still denote the sequence by the same symbol. Okay. So this is used frequently in analysis because we have sometimes to choose a subsequence of a subsequence, so the notation becomes cumbersome. So we may still denote the subsequence by the same symbol. Okay, and now I will get a contradiction. So the distance between fn of xn and fn of x0 by the triangular inequality. So I introduce fxn and fx0. So I have this. Now, the first term tends to 0. Why? Because fn converges to f uniformly. Okay, so this is actually less than delta fnf. And same thing here. Both the terms are less than delta fnf. And delta fnf, by our change of notations, converges to f. Okay? So if you wanted to write the subsequence, we would have written fnk and nk, nk, nk. So this simplifies a little bit, but doesn't change anything fundamental. So the first term and the third term are less than converge to 0. And what about the second term? The second term also converges to 0 because f is continuous and xn converge to x0. So this quantity converges to 0, but this quantity is bigger than epsilon 0, so we get a contradiction. Okay, if it's bigger or equal than a positive constant, it cannot converge to 0. Okay, this prevents conversion, so we get a contradiction. So we prove the first result. So equicontinuity is necessary for relative compactness. Okay, and you can ask if it's enough, it's sufficient. It's not sufficient. And now I'll give a counterexample. If we take the same space C01, we denote, this is the functional analysis notation. So in order to simplify, so C of 01 is just the space of continuous functions from the closed interval 01 to R. And consider this sequence of translates of the identity. Okay, so Fn of x is just x plus n. This family is equicontinuous. Why? Because Fn of x minus Fm of x, sorry, excuse me, Fn of x minus Fn of y, the n cancels, so we are left with x minus y. Okay, so it's Lipschitz equicontinuous if you like. So we can take alpha equal epsilon, as we may easily check. So this family is equicontinuous, but it's not relatively compact because it doesn't contain any convergent subsequence. So no matter what, so if you choose any subsequence nk, you'll get fnk equal x plus nk, and this cannot converge. This tends to infinity actually. So it's not convergent to any continuous function. So this means that equicontinuity is only necessary in order to, so we need another condition to guarantee relative compactness. And this is the second condition. If x, so as usual, if x is a compact metric space and calligraphic f is a subset of continuous functions from x to y, if it's relatively compact, then for each x, the set of images of x under all f is relatively, this is a subset of y, because f takes values on y. So relative compactness implies that for every x, this set is relatively compact in y. Okay. This is not difficult. How do I prove that this set is relatively compact? I fix the x first and consider a sequence in calligraphic fx. So this is necessarily something of the form fn of x. And I will prove that it has a convergent subsequence. Now, this is very easy, straightforward, because I assume that calligraphic f is relatively compact. So the sequence fn contains a subsequence fnk that converges uniformly, actually. But it's converged uniformly, then it converges pointwise. And therefore, fnk of x converges to f of x. So we found a subsequence of this sequence converging. Therefore, we proved the proposition. So very easy. And now we are ready to state. So observe why this didn't work here in this example. Because this collection is not relatively compact. It's unbounded, actually. Okay, when you fix x and you let n vary, you get an unbounded set of numbers. So this is why we didn't have relative compactness here. Okay, and now we are ready to state the Arzela-Ascoli theorem that, yes, these two conditions together are necessary and sufficient. Okay, so, but we have to assume, of course, that x is compact. We have always to assume that x is compact because in order to put a topology on Cxy. Now, we can put a topology on Cxy, but even if x is not compact, but it's a little bit more complicated. Here we are dealing with the fundamental form of Arzela-Ascoli. So in order to define the distance on Cxy, we have to assume that x is compact. And we have to assume that y is complete as well. So a collection of continuous functions from x to y in this context is relatively compact, so it has compact closure if and only if it is equicontinuous and therefore uniformly equicontinuous, as we know. And for every x, this set is relatively compact in Y. Okay. Now, if we want compactness, we just have to add the closedness of F. So F is compact if three conditions hold. It should be closed, equicontinuous, and for each F, for each x, this set is relatively compact. Okay, we already proved half of it, and now we want to prove the converse. Okay, so we assume that F satisfies these two conditions, and we prove that F is totally bounded. So given epsilon, we give ourselves a positive number epsilon, and we will cover F by finitely many balls of radius epsilon. Okay, so we know that F is uniformly continuous, actually. So there exists alpha positive, which depends only on epsilon, such that uniformly in F and uniformly in X and uniformly in Y, if the distance between X and Y is less than alpha, then the distance between their images is less than epsilon for all F in the collection. Okay. Now we can always write X as a union of open balls of standard X and reduced alpha. We used that before, and yeah, so we can just use total boundedness. Okay, so we can write X as a finite union of balls of reduced alpha. Okay, and now we will have to work in y times y times y n times. So we equip y to the n with the maximum distance. So as you know, this should be actually d sub y. Okay, so, and it's easy to prove that this distance generates the product topology, and since every y is complete, then y to the n is also complete. Okay, for fixed n. Okay, the same n that we took here. N is fixed here. Okay. Now, by the second condition, calligraphic f sub xi is relatively compact. Okay? So it's not difficult to prove that their product is also relatively compact, because the closure of the product is the product of the closures. And each one is compact, the product of compact is compact. Okay? So very straightforward. Therefore, it's totally bounded. Okay? Therefore, we can cover this product, fx1, etc., fxn, by finitely many balls. Of course, a point in this product is an n-tuple. Okay? So we can cover this product by a union of balls of center fjx1, etc., fjxn, and radius epsilon. Okay, and we'll prove that f is contained in the union of all these balls, but of radius 4 epsilon. Now, as you observe, 4 epsilon, 5 epsilon doesn't matter. If I wanted exactly epsilon here, I should have taken here epsilon over 4. Okay, so it doesn't really matter. And this will prove my claim. This proves exactly that f is relatively compact or totally bounded. Okay. So how do I prove this? I take an element here and prove that it's here. So take an element small f in this collection and pick a point small x in this space. Okay, according to what we said before in this previous slide, capital X is the union of balls of center xi and radius alpha. So we can find an integer I such that the distance between x and xi is less than alpha. Okay. And according to what we said here, we can cover this product by finitely many balls, m balls actually. So we can find a ball of center fjx1, etc., fjxn that contains this element f of x1, f of x. So the distance between f of xi and fj of xi is less than epsilon by definition of the ball. Okay, we're almost done. So now I use the triangle inequality, okay, to prove that f is here I estimate the distance between f and fj at x first. So the distance between fx and fjx by the triangle inequality is less than the sum of these three terms. So I introduce f of xi and fj of xi. Now the first and third term are less than epsilon. Why? Because the distance between x and xi is less than alpha. So the condition of equicontinuity tells me that, and same thing here, and so by equicontinuity tells me that this is less than epsilon and this is also less than epsilon, okay? Because this happens for every element f in the collection. Okay, now what about, yeah, so the second term is also less than epsilon by what you said, because of this actually. So the sum is less than 3 epsilon, and that this is true for every x. So the supremum over x is less or equal than 3 epsilon. So the delta of f and fj is less or equal than 3 epsilon, and therefore it's less strictly than 4 epsilon, and therefore f is here. So we found one j bit from 1 to m whose distance to f is less than strictly 4 epsilon. So this proves total boundedness of f. Okay, so as a corollary, if we take y to be Rn, we can formulate the same theorem. In particular, relative compactness of a subset from the space of continuous functions from a compact metric space X into Rn is relatively compact if two conditions hold. It's equicontinuous, and for each X, the set of images of X under all elements of the family is bounded. Okay? Because we know that boundedness in Rn is equivalent to total boundedness. And I will end with a theorem, with an example. Fix a positive number m and consider in the space of continuous functions from 0, 1 to r the subset of all C1 functions that vanish at 0 and whose derivative is less than this m. Okay? Then this collection is actually relatively compact. Okay? Why? The same reasoning, the mean value theorem that we used actually proves equicontinuity. And actually, this condition that f of 0 equals 0 implies, you have to check that actually, implies boundedness of the set of all fx when f varies. Okay, you have to check this. And so this is easy. Check that. However, f is not closed, and so it's relatively compact but not compact. So you have two things to do now. Check that this second condition is satisfied. And second thing, more challenging, what is the closure of this set? This is a difficult question. It's not closed. You understand why it's not closed. You can prove that it's not closed. So first, prove that it's not closed and find its closure. Okay, so 3 questions as an exercise. So this concludes this video and section 1.1 about the Arzela-Ascoli theorem. And in the next video, I will be solving some exercises. But I suggest first that you try to solve them on your own before we solve them. So thank you for your attention and see you next time.